This is a walkthrough of Problem 3 on Practice Exam 1 of Module 10 in the book Problem Solving Guide for Mechanics and Thermodynamics. We have 100 grams of ice at 0, 100 grams of steam at 100 degrees, and we put them in a chamber and we let them fight it out. And we want to know who wins. Let's sketch what's going on. We have some ice at 0, 100 grams. We have some steam in a box at 100 degrees Celsius, mass 100 grams. We put them together, and they're probably going to have some water. What's the final temperature? What's going on in here after they come to equilibrium? It's a nice problem. We have to really understand what's going on. What's the equilibrium situation? What does that look like? Can we describe it? Is there any ice left? Is there any steam left? We have to explore. We have to figure it out. We're going to start with the latent heat of fusion and the latent heat of vaporization of water. Latent heat of fusion of water, 334,000 joules for every kilogram. And latent heat of vaporization is 2,260,000 joules per kilogram. My money is on the steam. So let's start by determining how much energy it takes to take 100 grams of ice at 0 to 100 grams of water at 0. We're just melting the ice. We're not changing the temperature. It's a phase change. 334,000 joules every kilogram times a tenth of a kilogram, which is 100 grams, 33,400 joules. That's to take the 100 grams of ice at 0 to 100 grams of water at 0. Now let's determine how much energy it takes to take 100 grams of steam at 100 degrees Celsius to 100 grams of water at 100 degrees Celsius. 226,400 joules. Does the ice have that much? We're going to find out. Steam's going to win. My money's on the steam. Now let's calculate how much steam has to condense to melt all the ice. We know how much energy costs. It costs 33,400 joules. How much steam has to condense to get that much energy out? So 33,400 joules, that's how much you get. And then we have the mass when we condense steam, 14.8 grams. So of the 100 grams of steam, we turn that steam, 14.8 grams of steam into water, and we just melted all the ice. Okay? So now we have 100 grams of melted ice. It's still at 0. We have about 15 grams of water, condensed steam, and we still have 85 grams of steam left at 100 degrees Celsius. All right, so now we can heat up the melted ice with that steam. Let's see how far we can get it. Let's determine the energy it needs to take 100 grams of water at 0 degrees Celsius to 100 grams of water at 100 degrees Celsius. We're not doing any phase change. We're taking the water that we just melted. It's at 0. We're going to take it to 100. So it's MC delta T. And we calculate that, and that's 41,840 joules. How much steam do we have to condense to get that much energy out? So there's the latent heat of vaporization for water. That's how much energy we need to take 100 grams of water at 0 to water at 100. 18.5 grams only. So we melted the ice, then we took the water from 0 to 100, and we still have steam left. And they're all at the same temperature. Everything's at the same temperature. Everything's at 100. So the final equilibrium temperature is 100 degrees Celsius. And how much water did we condense? 18.5, I forgot. 18.5 and 14.8, 33.3. So we still have 66.7 grams of steam. 133 grams of water. 100 grams of it was from the ice that melted. 33.3 grams of it is from the steam we condensed. We condensed 14.8 to melt the ice. We condensed 18.5 to get that water from 0 to 100. Now everything's at 100, and if it's all at the same temperature, it's in equilibrium. No more heat's going to flow. So that's the final situation. It's at 100 degrees. There's 133.3 grams of water and 66.7 grams of steam. That's a nice one. That's problem 3.